In this video, we're going to talk about blood pressure, but I want to go backwards a little bit and review a couple things. So cardiac output is heart rate times stroke volume. Heart rate is the number of time a heart contracts in a minute, or the number of cardiac cycles a minute, and we call that beats per minute. The effector of heart rate is the SA node. Remember that the SA node initiates each cardiac cycle, so the rate at which the SA node fires determines heart rate. Stroke volume is the volume of blood that comes out of the left ventricle with each contraction or each beat, and we express that in milliliters per beat, sometimes just milliliters. So the definition is the volume of blood that comes out with each beat. The effector for stroke volume is the left ventricular myocardium, because the myocardium, depending on how strongly the myocardium contracts, the left ventricle is going to squeeze harder. If it squeezes harder, it ejects more blood. So stronger contraction of the left ventricular myocardium would increase stroke volume. So during exercise, we get an increase in heart rate, we get an increase in stroke volume, and because those two things affect cardiac output, we get an increase in cardiac output. Okay, and cardiac output is basically blood flow. And during exercise with higher demands, we need a higher supply. So we need an increase in blood flow during exercise. So together, an increase in heart rate and an increase in stroke volume results in greater blood flow per minute in the body. Cardiac output is usually expressed in liters per minute, not milliliters per minute. So you would have to take that value and convert it into liters. So blood pressure is the pressure exerted on the walls of your blood vessels. When we talk about blood pressure, we're usually talking about arterial blood pressure. Systolic blood pressure is the pressure in the arteries during ventricular systole. It's the highest pressure during the cardiac cycle. A normal systolic blood pressure would be 120. The diastolic blood pressure is the pressure in the arteries during ventricular diastole, or when the ventricle is relaxing and not ejecting blood. This is the lowest pressure of the cardiac cycle, and a normal diastolic blood pressure would be 80. So it makes sense that when blood is coming out of the left ventricle, as it is during systole, there's a lot of pressure being exerted on the artery walls. But when the left ventricle is at rest and refilling and there's no blood coming into the arteries, the pressure is going to be lower in the arteries. Hypertension is defined as high blood pressure, and the cutoff is a systolic of 140 or a diastolic pressure of 90. And blood pressure is measured in milliliters of mercury. So we've established that the pressure changes across the system. When you look at the pressure in the left ventricle, it's very high. It's about 120 millimeters of mercury. And we said earlier that the pressure in the aorta is about 100. And as we move through the system, from your left ventricle to your aorta, to your arteries, to your arterioles, your capillaries, your venules, your veins, we end up back in the right atrium with a pressure of about 0. So we've got this pressure gradient. This is P1, this is P2. Okay, the pressure here is much higher, and that's why blood flows from the arteries into the veins, because of this pressure gradient. So the primary reason for pressure differences across the system is a difference in resistance from the vessels themselves. Okay, and we call that peripheral resistance. Okay, peripheral resistance. It's the resistance of flow, the resistance of blood flowing forward. And we abbreviate it PR. And the three factors that affect peripheral resistance are the length of the vessel, the viscosity of the fluid in the vessel, and the radius of the vessel. And the way we explain it is with this formula here. Now, this is an important formula for you to use to understand the relationships between variables. It's not a formula that you will be using for any calculations. So we won't be putting numbers in this formula, but it's important for you to understand relationships. For instance, peripheral resistance is directly related to length and viscosity, but indirectly related to radius. Okay, so what that means is that if the length of a vessel increases, then the peripheral resistance is going to increase. And I like to use the example of a straw. Okay, if you are moving fluid through a straw, some straws are easier to move fluid through than others. It's harder to move fluid through a longer straw. If you have a 2-foot straw, you're going to have to do a lot more work to move the fluid through that straw than if you had a 3-inch straw. Okay, so as the vessel length, the vessel containing the fluid, which in our example was a straw, the vessel length goes up, peripheral resistance goes up. Then we have viscosity. So viscosity is the thickness of the fluid going through the vessel. So in our straw example, if you are sucking water through a straw, it's fairly easy to move that water. But if you are you're trying to drink a thick shake, the fluid in that straw is very viscous, and increased viscosity results in more resistance to flow, which makes sense, right? And the third factor is radius. So this is the radius of the vessel. And in this case, in our example again, this would be the radius of the straw. So if you've got one of those big straws like they have at McDonald's, it's really easy to drink a lot of fluid in a short period of time compared to maybe a cocktail straw, one of those tiny little red straws with very small radius. It would be much harder to drink the same volume of liquid through one of those smaller straws because there's more resistance to flow. So an increase in radius would result in a reduction in peripheral resistance. Okay. So vessel length is directly related to peripheral resistance, viscosity is directly related, but radius is indirectly or inversely related. And the same would be true if we did it the other way around. Okay, a decrease in vessel length would cause a decrease in peripheral resistance, decrease in viscosity, decrease in peripheral resistance, decrease in radius, increase in peripheral resistance. Okay, so these two values are on the top because they're directly related. This is on the bottom because it's indirectly or inversely related. Now I also want to point out here that radius affects peripheral resistance to the 4th power. And what that means is of those 3 variables, radius has a much more powerful effect on peripheral resistance, so that even small changes in radius are going to have a large effect on peripheral resistance. So it's important to understand peripheral resistance. We will come back to this as we talk about blood pressure. The other thing I wanted to talk about is flow rate. Okay, I think your textbook just calls it blood flow, but it's the rate of flow, or how fast the blood is flowing through your body. And flow rate is related to 2 factors. One is peripheral resistance, which we just talked about. And because peripheral resistance is on the bottom of this formula, that tells us that flow rate and peripheral resistance are inversely related. Okay, and what that means is if we increase peripheral resistance, we decrease flow rate. Okay, and at the same time, if we decrease peripheral resistance, we increase flow rate. So peripheral resistance has an effect on the rate of flow. So when we talk about exercise, it's important to increase the flow rate. So think about how you would want peripheral resistance to change during exercise. If you need the blood to flow at a faster rate, then during exercise you hope that peripheral resistance would decrease to help blood flow increase. And we'll come back to that. So the other factor in this formula that affects the rate of blood flow is the change in pressure. Okay, this is P1 minus P2. And in this case, it's the change in pressure from wherever the blood is starting to wherever it's ending. And in this case, the blood leaves the aorta and it ends up in the right atrium. So P1 is the pressure in the aorta, P2 is the right atrium. So delta pressure is P1 minus P2, okay, or the pressure in the aorta minus the pressure in the artery. And as I told you, the pressure in the aorta at rest is about 100, and in the right atrium, it's about 0. So delta pressure at rest is about 100. During exercise, again, we want flow rate to increase. And because pressure is directly related to flow rate, if we increase delta pressure, we're going to increase the flow rate, which is what we want to do during exercise. So the pressure in the right atria doesn't change during exercise, but what happens is the pressure in the aorta goes up. Okay? So pressure in the aorta may go up to 120 during exercise. So now delta pressure, instead of being 100 minus 0 with the change of 100, it's going to be 120 minus 0, and therefore our delta pressure, our change in pressure, or our pressure gradient is 120, which is higher, which means the blood is going to flow faster during exercise. All right, so let's talk about blood pressure. And we're going to talk about acute control of blood pressure. Your textbook talks about long-term control of blood pressure, but this semester we're just going to talk about acute control. So if there's a sudden increase or decrease in your blood pressure, how does your body respond on an acute or immediate basis? So to talk about blood pressure, it's important to understand the formula for cardiac output, which we've already talked about, and the formula for peripheral resistance, which we've already talked about. And now I'm going to add another formula, which is the formula for blood pressure. Okay. So there are two things that affect blood pressure: cardiac output and peripheral resistance. And you can see in this formula they are directly related to blood pressure. Okay, so what that means is if cardiac output goes up, blood pressure goes up. If peripheral resistance goes up, blood pressure goes up. Okay, so either a rise in cardiac output or a rise in peripheral resistance are going to result in an increase in blood pressure. On the other hand, if cardiac output goes down, blood pressure goes down, and if peripheral resistance goes down, blood pressure goes down. Therefore, in order to decrease blood pressure, you either need a reduction in cardiac output, a reduction in peripheral resistance, or both. So, based on this formula, let's talk about how we control blood pressure. Okay, so if we want to change blood pressure, we either have to change cardiac output or peripheral resistance, because those are the only two factors. Okay. So if we want to change cardiac output, we can do that by changing either heart rate or stroke volume. Okay, so if you want cardiac output to go up, you can increase heart rate, or you can increase stroke volume, or both. And if cardiac output goes up, blood pressure is going to go up. Okay, So heart rate and stroke volume affect cardiac output. Cardiac output affects blood pressure. So those are two ways that we can change blood pressure on an acute basis. We can change heart rate, we can change stroke volume. Both of those things are going to have an effect on blood pressure. The other factor is peripheral resistance. Okay? And peripheral resistance is related to three factors: length, viscosity, and radius. But remember that we're talking about acute control. So we're talking about something the body can do in a matter of minutes. Okay? And in a matter of minutes, the body cannot change the length of your vessels. And the body cannot change the viscosity of your blood. So on an acute basis, the only way the body can change peripheral resistance is by changing the radius. Okay, the radius of those vessels. And the vessels that we're talking about here are the arterioles. Okay, so if you want to change peripheral resistance, you change radius. If you want to increase peripheral resistance, you would decrease radius. If you want to decrease peripheral resistance, you would increase radius, because they are inversely related. So let's go to these three factors. So if you want to change heart rate, you need to send a signal to the effector. Okay, and we've already established that the effector of heart rate is the SA node, and the rate at which the SA node fires. The effector of stroke volume is the left ventricular myocardium, okay, the muscle in the walls of the left ventricle and how strong that muscle contracts. And the effector of arterial radius is the smooth muscle in the walls of the arterioles. Because remember that we can cause smooth muscle to contract. That's vasoconstriction, which would reduce the radius. We can also have smooth muscle relax, which would be vasodilation, which would increase radius. So we have the ability to change heart rate, stroke volume, and radius very quickly by modifying heart rate, stroke volume, or radius. So if you want to increase heart rate, what you would want to do is increase the firing rate. So the response of the SA node is the SA node firing rate. Okay, so the effector is the SA node, the response is the firing rate. For the myocardium, the effector is the myocardium, the muscle again, and the effector response is going to be contraction strength, how strongly the myocardium contracts. And then the response of the smooth muscle in the arterioles is either going to be for that smooth muscle to contract and cause constriction, or relax and cause dilation. Okay? So we can tell an SA node to either fire faster or slower. We can tell the left ventricular myocardium how strong to contract, and we can tell smooth muscle to either contract or relax. And by manipulating these effectors, we can manipulate these factors, and therefore we can manipulate blood pressure, which is our goal here. So now I'm going to go back to chapter 3 when we talked about the nervous system. And remember, we talked about sensory motor integration, and we talked about these factors. Okay? And so we're going to go back to these same factors in this example. So in this example, which we also talked about in chapter 3, we have a stimulus, which in this case was an increase in room temperature. We have a sensory receptor, which was the thermometer. that's measuring the temperature in the room and is stimulated when it recognizes a change in temperature. We've got the sensory wire that carries the signal from the thermometer to the integrating center, which is the computer, which reads that incoming message, interprets it, and decides what needs to be done. Sends out information about the response through a motor wire, which is received by one or more effectors, and the effectors are told what to do. So in this case, because we have an increase in room temperature, the integrating center has determined that what we need to do is turn the furnace off, okay? Turn the air conditioner on, okay? And what the effector response, okay, these are the effectors. The effector response is that the air conditioner is going to start putting out cold air, the furnace is going to stop putting out hot air, and our final result is a decrease in room temperature, which negates the original stimulus, and we have negative feedback. Okay? So what you're going to do in your assignment is going to be to map out acute control of blood pressure in this same way. So you're going to have to identify, well, I'm going to give you the stimulus. You're going to have to identify the sensory receptor, the sensory neuron, the integrating center, the motor neuron, the effectors, because there's going to be multiple, the responses, because they're going to be multiple, and the final result, which results in negative feedback. And you are going to color code your assignment the same way I've color coded this example. All right, so for blood pressure, for my example today, what I'm going to do is I'm going to give you a stimulus, and I'll do the same thing for your assignment. The stimulus is an increase in blood pressure. Okay? Disrupts homeostasis. It's detected by sensory receptors. So what do you think is the sensory receptor for blood pressure? Okay. It would be a pressure receptor. Baroreceptors. Okay, so the baroreceptors are located in your aortic arch and in your carotid arteries. And they're constantly monitoring the pressure. And when pressure changes, they send a signal, an action potential, through sensory neurons to the integrating center. And the cardiovascular control center in the brain is located in the medulla oblongata. So the medulla oblongata receives this action potential, interprets it, determines what needs to be done, sends a signal out through autonomic motor neurons. Now, these neurons are either going to be parasympathetic, which would be the vagus nerve, or sympathetic, which would be the sympathetic cardiac nerve. Okay, we talked about these earlier in this chapter. The effectors, there's three possible effectors, which we talked about on the last slide, which are the SA node, the left ventricular myocardium, and the arterial smooth muscle. Okay, so you have three effectors. Okay, we're trying to control blood pressure. Remember, blood pressure is cardiac output times peripheral resistance. Cardiac output is heart rate times stroke volume. And peripheral resistance is length times viscosity over radius to the fourth. But we've established that length and viscosity cannot affect blood pressure on an acute basis. So the three responses we have to choose from are change heart rate, change stroke volume, change radius. Okay? So the SA node is capable of changing heart rate. The left ventricular myocardium is capable of changing stroke volume. And the arterial muscle, smooth muscle, is capable of changing radius. So the effector response is going to be the direct tissue response. So in this example, blood pressure is up. We want to bring blood pressure down. Okay? In order to bring blood pressure down, we need a decrease in cardiac output and a decrease in peripheral resistance. In order to decrease cardiac output, we can decrease heart rate and stroke volume. In order to decrease peripheral resistance, we can increase radius. Okay? So, if you want to decrease heart rate, your effector response is going to be to tell the SA node to fire at a slower rate. Okay? If it fires at a slower rate, you're going to get a reduction in heart rate and a reduction in cardiac output, therefore a reduction in blood pressure. For the left ventricular myocardium, okay, if we want to reduce blood pressure, so we want to reduce stroke volume. So the effector response is going to be that you tell the left ventricular myocardium you're going to remove some of the sympathetic output to the left ventricular myocardium. Okay, so you withdraw some of the sympathetic. Remember that the the vagus nerve does not go to the left ventricular myocardium. So actually going backwards a step here. So if we want the SA node to slow its rate, okay, you would start sending more signals through the vagus nerve, right? Reduce sympathetic cardiac nerve output, increase vagus output, and what you're going to get is a reduced firing rate, a reduced heart rate, therefore reduced cardiac output, reduced blood pressure. Now for the myocardium, the vagus nerve does not go to the left ventricular myocardium. So all signals to the left ventricular myocardium are going to come from the sympathetic nerve. And we've already established that we are going to reduce some of the action potentials going out through the sympathetic nerve. The left ventricular myocardium is going to receive less sympathetic action potentials, and therefore it is going to reduce its contraction strength. So this is firing rate. This is contraction strength. Okay, these are the responses. If you reduce contraction strength, you reduce stroke volume. If you reduce stroke volume, you reduce cardiac output. And if you reduce cardiac output, you reduce blood pressure. Okay? So two different effectors working on the same response. So let's look at the third effector, the arterial smooth muscle. So the arterial smooth muscle, like the left ventricular myocardium, does not receive sympathetic action potentials. It only does not receive parasympathetic action potentials. It only receives sympathetic. So if you want the arterial radius to go up, we need those arterioles to relax. And in order to get the arterioles to relax, we are going to pull back some of those sympathetic action potentials. Okay, so by sending less sympathetic cardiac nerve output, the arterial smooth muscle is going to relax. Okay? And the secondary response is going to be an increase in radius. An increase in radius decreases peripheral resistance, and a decrease in peripheral resistance again increases blood pressure. Okay? So we have 3 different factors affecting this reduction in blood pressure. There's our negative feedback. Let me give you a little bit of direction because this concept map is going to be fairly complicated compared to the view. So obviously at the top you're going to have your stimulus, and I will give you that. You are going to have your receptors, which are the baroreceptors, and I want you to indicate where they are. And you're going to have your sensory neuron. You're going to have your integrating center, which is your medulla oblongata. And coming out of that, you have 2 possible nerves, right? You've got sympathetic output, and you have parasympathetic output. Okay. And you have 3 possible effectors, right? You have your SA node, you have your left ventricular myocardium, and you have your arterial smooth muscle. I'm abbreviating here. Obviously you would write these words out. So depending on, and remember that the parasympathetic nerve goes to the SA node. The sympathetic nerve goes to all 3. Okay? But the parasympathetic only goes to the SA node. All right. So we have 3 possible effectors, and if we have an increase in blood pressure, you need to change the output. So what you're going to do is you are going to reduce sympathetic output and add parasympathetic output. Okay. And I'm not going to finish this for you, but below your effectors, you're going to have the effector responses. So this is going to change firing rate of the SA node, which is going to change heart rate, which is going to change cardiac output, which is going to reduce blood pressure, which is your final response. Okay. The left ventricular myocardium is going to contract with less force. That is the response. The secondary response is going to be a reduction in stroke volume, which causes a reduction in cardiac output, which leads to the final response, which is a reduction in blood pressure. And finally, if you send less SNS output to the arterial smooth muscle, you get a relaxation or vasodilation of the arterial smooth muscle. The secondary response is an increase in vessel radius, and that causes a decrease in peripheral resistance, which decreases blood pressure. So remember, blood pressure, we have heart rate, we have stroke volume, and we have length times viscosity over radius. Okay. But here we're talking a radius. So smooth muscle is going to affect radius, which is going to affect peripheral resistance, which affects blood pressure. Heart rate and stroke volume affect cardiac output, which affect blood pressure. Okay. because blood pressure is cardiac output times peripheral resistance. Okay? Cardiac output is heart rate times stroke volume, and peripheral resistance is affected by radius.